All right. So this was the first one I was asked about here. It's from chapter 28. It's number 6 in your homework. So if you want to look up the exact wording of this, you can. But essentially, there were two speakers, and they were a certain distance away from Larry, Mo, and Curly. And you're supposed to find where Curly here, Curly or Mo, they're the same distance away from Larry, where they would hear the least amount of sound. So that means we were looking for destructive interference. So the first thing I did here was figure out how far. I just went with Curly. It didn't really matter whether you did Curly or Mo because the answer is going to be the same for both of them. So I went with Curly up there. I made right triangles in order to figure out how far Curly was from each of the two speakers. So here was one speaker, here was the other speaker. Their distance apart I called S, which was given as 0.8 meters. And their distance, the distance like Larry was and these three guys were in a straight line across from the speakers was 3 meters, which I called capital D. They called this like the distance from Larry to Curly or Larry to Mo. They called that little d, and they said that was 1.6 meters. So those were our given information. Here, I said this was the distance from the bottom speaker up to Curly. I called it R1. And so it makes a right triangle with D. And then this little part here, you know, is going to do it, which is going to end up being the length D plus half right here, half of this 0.8 meters right there. And so doing that, I can do Pythagorean theorem, and I get this right here, D squared plus D little d plus 0.4 meters squared square rooted is what R is. So that's my right triangle for finding the distance from the bottom speaker. For the top speaker, I used this right triangle right here, which again, this bottom part is still the capital D. And then this side over here is going to be the lowercase letter d, the 1.6 meters, minus this little half of S, that point, so minus the 0.4 meters, which is what I put right here. And I did the Pythagorean again, so capital D plus D minus the 0.4 meters squared, all square rooted. And so that gives me each one of them in their length. So this one turned out to be square root of 13 meters, and this one's turned out to be square root of 10.44 meters. Neither one of those is a real pretty number, so I'm just going to leave them like that. Now here, again, we were looking for destructive interference because we were looking for where it was lowest, and we were all, or where it was softest, quietest. And so we were also looking for the lowest frequency that would do this. So we need the lowest frequency that's going to do this is going to have a wavelength difference, a path length difference of 1/2 lambda. So what that means is that the difference between our two distances, R1 and R2, so the distance that Curly is from each speaker, has to equal 1/2 of the wavelength. Since up above we use Pythagorean theorem to solve for those two distances, I simply plug them in right here, the square root of 13 and then the square root of 10.44, multiply the 2 over from the 1/2. And so I get that the wavelength is 2 times the square root of 13 minus the square root of 10.44 meters. Now, after that, it's just then, that tells me only the wavelength. The question, though, wanted the frequency. So we use V equals F lambda right there. Solve it for F, and that equals V over lambda. And then it's just a matter of plugging that in. I know it's sound, so I went 343 meters per second for that. And then lambda was 2 times this. That was what the wavelength was. So I just plugged that in there in the bottom. And then it was just a matter of plugging those things into a calculator. 343 divided by 2 times the difference of those two square roots. Once I did that, it gave me 458 hertz. The problem wanted you to give it, I think it was with 2 significant figures. So I went with 460 hertz, or you could also make that 0.46 kilohertz. So either one of those, that right there is the lowest frequency that will work. So, you know, one of these two, I don't know which one the homework actually wants, but they're the same thing. So those answers right there. Now we also want the second lowest frequency, which means we want to go through and find not when we're equal to 1/2 lambda, but when we're equal to 1.5 wavelengths. So that's the very next one that we're off by, which is essentially 3/2 lambda, right? That's what 1.5 is 3/2. And so then I just went through and I did the exact same thing that I did over here, except this time, instead of this 1/2 right here, I put 3/2 right there. And so instead of having this 2 right over here, I end up with this 2/3 over there. And so I just solved it the exact same way, go through the same process. And this time I got, rounding off the 2 sig figs, 1400 hertz or 1.4 kilohertz. And so those are the 2 lowest ones that we could have there. Are there any questions on this one specifically before I move on? No? That one made sense then, okay? All right, I'm gonna move on then. If you need me to go back later, I will. This was the next one that was asked. And this is chapter 28 again, number 28. And here what we have is a thin film on some material. I can't remember what, it was glass. So we had air, and then I think we had soap, and then glass, making us a thin film of the soap, but it was on top of the glass. So what that means is on the reflection coming at the top, we're going from a low index to a high index. That means we're going from high speed, right? High speed up here to low speed down here. All right, maybe I can write that out. This is high speed to low speed or lower speed, right? And so what that means is that we will get a phase change that acts just like, there should be an E on that. That acts just like the fixed boundary. The lower speed, you can think of it, it doesn't react fast enough in order to move. So it's kind of acts like that fixed boundary off the reflection. And so we get an inversion, which means we get that phase change. However, we also get another phase change on the next one, because here we have an index of refraction of, let me get rid of all this, of 1.33 going into 1.52. And so now again, we're going from a low index to a higher index. So again, we're going from a high speed to low speed, because remember, the lower the index, the higher the speed. So we're again going from high speed to low speed, which means we're going to get another phase change. That means we have 2 phase changes. So that essentially means they're both going through a phase change, and then we don't really have to worry about the phase changes anymore. And you remember that the equations given in the book, they're designed, the ones given, for a single phase change. Since we have 2 phase changes, we have to swap what they're for. So if you look at the equations in the book, this equation right here is given for, we're trying to do, I think we're trying to do, we're trying to do constructive interference, but this equation is given for destructive interference when there's just a single phase change. Since we have 2 phase changes, the 2 phase changes cancel each other out. And so we go right back to needing a full path length difference. So we choose the one without the -1/2 in it. All right, without the 1/2 in it. And so we end up using the one for destructive interference if there were 2 phase changes, but we're using it for constructive interference because we have 2 phase changes. So the 2 phase changes, They cancel each other out. Now this asked also for us to figure out what wavelengths of visible light will constructively interfere in this situation. And so visible light goes from 380 nanometers to 700 nanometers. And so I just went ahead and started with m equals 0. Well, at m equals 0, we really kind of don't have anything interesting there because that basically implies that t equals 0. And so we don't have any kind of a film, but we do actually have a film thickness. So we don't need to worry about that one. So if we look at m equals 1, we solve our equation up above for lambda. So that equals 2 nt over 1. This time, it's, just the one, it makes it pretty easy. So it's 2 times 1.33, which is the index of refraction here of the soap right up there. And then times 648 nanometers, that's the thickness of the film. And so a nano means 10 to the negative 9. So that's 648 times 10 to the negative 9th meters. Type those in your calculator, hit enter, and you should get this answer right here. This answer is not, all right, it's going to be not inside the visible range because this answer being at 10 to the negative 6, we'd have to move the decimal place 3 places to the right. So this would be 1720 times 10 to the negative 9 meters. So it's 1,720 nanometers, that answer, which means that that is outside our visible spectrum. It would be, it's greater than 700 nanometers. So that one's out. It's not visible. If we go to m equals 2, we do the exact same thing, but this time we divide it by 2 instead of divided by 1. And so when you do that, you get this 8.6 times 10 to the negative 7th. So that becomes 860 nanometers. And that is also greater than 700 nanometers and is therefore outside the visible spectrum. So then we try n equals 3. So we put a 3 in the denominator this time, calculate the same thing out, and you get 5.75 times 10 to the negative 7th meters, which is 575 nanometers. That is between 380 and 700 nanometers. So that one works, hence my check mark. That is in the visible range of light. Go to m equals 4. And we see that when we divide it by 4 this time, we end up with 4.31 times 10 to the negative 7th meters, which is 431 nanometers and is again inside the visible range of light. If we go to m equals 5, we get that right there. We divide it by 5. We get 3.44 times 10 to the negative 7th, which would be 344 nanometers for the wavelength, which is less than that 380 up there, which means we are now essentially we are again outside the visible wavelength spectrum. So anything else we do above or below it, if we keep going to m equals 6 or 7 or anything bigger than that, it's just going to keep making our wavelength shorter and shorter. And so we have those two answers right there. Those are the only two visible wavelengths that will interfere constructively in that situation. All right. Any questions on that one?
When do you switch the equations, like you use the opposite one like you were saying at the beginning?
Yeah, see, I didn't like that about you. So your book made it so that they made the equations for a single phase change. So if there's a single phase change, either here or here, there's just one, then you use the exact equations given in the book for constructive and destructive, just or even the way they're given in the notes for constructive or destructive, and you use them just as they are. If there are no phase changes or two phase changes, then no phase changes means you don't have to worry about the phase change, and two phase changes mean the phase changes cancel each other out. Because one of them gets switched from like a crest to a trough, but then so does the other one. So it cancels itself out. And in that case, or those two cases, you use the destructive one for constructive and you use the constructive one for destructive. You flip them. You switch them then in that case, or in those two cases. Does that make sense?
Yeah.
Like this one right here looks like destructive interference because we don't have that 1/2 in there. We usually have that like plus a 1/2 or minus a 1/2 whenever it's destructive interference, right? And so if you look at the one with a single phase change, it had, the constructive version has a 1/2 in it, because without that phase change, that would be the requirement for destructive interference. Basically, use them like they are if there's one phase change, swap them if there's two phase changes or no phase changes. Okay?
Yes, thank you.
Mm-hmm. Anybody else? All right, I'm going to go to the next one then. Here, again, chapter 28, number 29. In this one, there was a radio tower, and it was a certain distance D away from a radio, and it was 36 kilometers away. It stated that there was an airplane flying somewhere at a height H equals 2.21 kilometers above the ground there, and it was somewhere between, or didn't even, I'm not even sure it even said between, but it was just somewhere that high off the ground near both of these things. It stated that, what was it? It was that it said that it was the path length difference between the light or the radio signal that went up to the plane, bounced off the plane and came to the radio, and the path just straight to the radio from the tower had a path length difference of 90 wavelengths, so 90 lambda. Then it asked, was this destructive or constructive interference then when it reached the radio finally? Well, they're off by an integer number of wavelengths, this 90 lambda. However, when the radio signal bounces off of the airplane, it's going from air, which has an index of refraction of 1, and then it's bouncing off the airplane, which has to have an index of refraction higher than 1. And so therefore, we're going to get a phase shift because it's going from high speed to low speed inside the plane, high speed in the air. So we therefore get a phase change, which means if their path length difference is an integer number of wavelengths, it means they're really off by half a wavelength because one of the wavelengths got inverted. One of this wave up here got flipped over, and so they're actually out of phase then at that point, and therefore we're going to get destructive interference. All right, does that make sense to everybody? That's how you have to think through those ones. Okay. The next part then asked or told that the airplane was actually 2/3 of the distance between the radio tower, the broadcast tower, and the actual radio itself. And if that is the case, it wanted us to figure out what the wavelength of the radio signal was. And so to do that, I need to find the difference between the two paths. The straight path from the radio tower to the radio is 36 kilometers, which is this 36,000 meters. The path that the reflected waves take is this upper path up here, which is what I called RP, which was the distance from the radio tower to the plane. And then I called RR the distance from the plane to the radio. So that would be RP plus RR. And the difference between those two, I did an absolute value of around them, has to be equal to 90 lambda, because we were already told it was a path length difference of 90 wavelengths. So I'm going to use Pythagorean theorem to solve for RP, the distance from the radio tower to the plane. So this little part down here, since we know it's 2/3 of the way, that's 2/3 D. And then I know this height here is 2.21 kilometers. So I just left it and called it H. And I plugged that in right here for the, right there, you just plug those numbers in, plug in 2/3 times 36 kilometers and then square it, and then do 2.24 and square it and take the square root and you'll get that length. Then for the other one, again, I did a height of H squared, but then this distance over here is 1/3 D. So I put in 1/3 D right there. And again, Pythagorean theorem and square root it. And that gives me those two lengths. You can just plug those numbers into your calculator. And then I came down here and I said, all right, that has to equal the difference between them from right up here is equal to this 90 lambda. And so I divided both sides by 90 and I get lambda equals this, the difference between them over 90. So go ahead, plug in all the numbers. I was leaving that for you, for y'all. I did, but I didn't want to write it all out. And you should get 3.37 meters if you plug in all those numbers and take the square roots and all that kind of stuff. Okay, any questions on that one? No questions on that one? And that should be your final. Okay. And then the last one I believe that was sent to me was this one. For this one, we had two speakers. All right, we had this speaker, and they were a distance D apart, which was 0.894 meters. And then we were told there was a microphone that was a distance of 2.83 meters away from the center of the two speakers. All right. And so that was my situation there. They wanted us to find what wavelengths, or ultimately actually what frequency, the two lowest frequencies that would create constructive interference at the location of the microphone. So in order to do this, we are looking for the lowest frequency. We're going to look for the lowest one that we can have, which is our lowest path length difference of just lambda. If there's a path length difference of just lambda, then that means that they are going to have constructive interference, which is what we're looking for. So by saying that, what we're saying is that lambda has to equal B minus A, where B is the distance from this back speaker all the way to the microphone, and A is the distance from the front speaker to the microphone. That difference right there is that distance right there. So I wrote it out here mathematically for you. One of those distances is L plus D over 2. The other is L minus D over 2. So the distance between them is just D. But that should make sense because that's just, if you're just looking at the picture, that's just the distance between the two speakers. So that's our path length difference right there. That's our wavelength difference right there. So lambda simply has to equal the distance between the two speakers then at that point for the lowest frequency with constructive interference. So we come down here and we use V equals F lambda, that's our velocity equals frequency times wavelength, to find the frequency from the wavelength. So our lowest frequency corresponds to our longest wavelength right here, which is that distance D, because it's in the denominator. They are inversely proportional to each other. And so the speed of sound is 343 meters per second. And we just found that that longest distance that'll give us a path length difference of 1 lambda is simply the distance between the two speakers, or D. So you plug those numbers in, 343 divided by 0.894 meters, and you get 384 hertz. And so that's the answer right there for the lowest frequency that'll do it. The second lowest that will do it has to have a path length difference of 2 lambda. This will give us the second longest wavelength that does it, that will interfere constructively. So again, it's that B minus A whole thing. And that means that essentially 2 times lambda has to equal the distance between the 2 speakers. So 2 lambda equals the difference in the distances. So 2 lambda equals D. So lambda then equals D over 2 this time. Instead of just D like it was back then, it's D over 2. And we go through and we get frequency 2, again using V equals F lambda. So we're using this same thing right here. V equals F lambda gives us F equals V over lambda, which is V over D over 2, which then dividing by D over 2 is multiplying by 2 over D. That gives us 2V over D. So the difference here is it's going to be twice what the other one was. It's going to be 2 times 343 divided by the 0.894 meters. And that'll give us the 767 hertz for that frequency. Okay. Are there any questions on that one? No questions? Okay, I'm going to pause this for a second and see if we can get any other questions from you also. All right, and so red and violet light are incident on the prism at right angles to the vertical side. Given that the index of refraction of flint glass is 1.66 for red light and 1.7 for violet light, find the angle each ray makes with the horizontal as it emerges from the prism. So we need to look at some geometry here. We know it's coming in at a right angle to this back side or this vertical side of the prism, which means it's coming in perfectly perpendicular to it, which means there's no bending that occurs there. So we don't have to worry about it. The red and the violet both go through unchanged. However, when they reach this front edge right here, they're both hitting that at an angle. And so we have to figure out what their angle is to the normal, because that's the way we always measure these. So that's what I did right here. I drew in this normal line, and then I figured out what the angle was. And based on just some geometry, that angle has to be, this angle in here has to be 30 degrees. Okay? If you just think about it, you should be able to figure it out, because I guess if you think about it here, I guess I can do it real quick. This is 90 degrees right here because it's normal. This right here has to be 60 degrees because this is 90 degrees, and that's another smaller 30, 60, 90 degree triangle. So if this is 60 and this is 90, the leftover part right there is 30. Okay, so there you go. That's 30 degrees. All right, so since that is 30 degrees, that means our angle of incidence is going to be that. And then we have to figure out what angles does each refract to. Okay, and then they, of course, want us to tell them it relative to the horizontal. So we'll have to figure that out too. So we're going to use Snell's law, which tells us the angle of incidence times the sine, the index refraction of the incident material times the sine of the incident angle is equal to the index of refraction of the refracting material times the sine of the refracting, or the angle of refraction. And so here we're going to want to solve for theta 2, which is the angle it refracts to. So theta 2 will equal the arc sine of n1 times sine theta 1 over n2. So I just divided both sides by n2 and then took the arc sine of both sides. So going over here for violet light to the left, theta 2 would be the angle for the violet, which is what I labeled that up here, theta v. And so theta V is the arc sine of 1.7, which is the index of refraction of that of our material for violet light. So I put 1.7 in right there. The incident angle is 30 degrees and the incident material is air and it has an index of refraction of 1.00. So I plug those numbers in and I get a refracting angle of 58.21. However, they don't ask for the refracted angle. They ask for the angle with the horizontal. So what that means is I have to come up here and say, all right, I've got this whole angle here. This is my 58 degrees. And I have to take off that 30 degrees to leave me with this angle right here, which is the angle to the horizontal. All right, and so that's what I did right there. I did theta V, our angle of refraction for the violet light minus 30 degrees, and that equals the 28.2 degrees right there. Then I came over here for the red light, and I did theta R equals arc sine. This time, I used the index of refraction of 1.66 because that's what it was given to us for red light right there. And, excuse me, and I plugged that in, sine again of the incident angle of 30 degrees, and the incident material, which was air, has an index of refraction of just 1.00. So I really only just changed this one number right there and then redid the problem. This time it gave me 56.1 degrees. I did the same thing of subtracting off the 30 degrees so that I got it from the horizontal rather than from the normal, and it was 26.1 degrees. Okay, how's that?
That makes sense. I was just stuck on it was coming in straight, so I didn't want it to bend, but I didn't think about the other side being bent.
Yeah, it's not going to bend when it comes in straight. It bends when it exits because that's at an angle.
Okay, that makes sense.
Okay.